Today we're going to discuss the operation of the transformer and the associated rectification and regulating circuitry in the BRT400 radio receiver. If Thomas Edison would have had it his way, there would be no transformers at all in the world. The world would run on direct current of DC. The transformers only work for the alternating current. Here's the actual schematics of the BRT400 receiver's power supply section. There is a very substantial transformer in the set, shown here. A transformer normally has one primary winding and one secondary winding. However, there can be an infinite number of variations. Also, in principle, there's nothing to prevent the transformer being used, quote, in reverse, that is, changing the primary for the secondary and vice versa. All normal consumer equipment must be fully isolated from the mains. But for instance, most over 30 years old European television sets may lack the transformer, and thus the set's internals may be energized, depending on the way the power plug is inserted into the wall outlet. These sets are isolated by passive means, making it impossible to touch the internals and the chassis under normal use. In the diagram, we see that there's a mains switch and two fuses on either mains line. The mains also can be connected to the 110 volts point. The wiring inside the transformer for the 110 volts has then to be twice as heavy as the rest of the primary winding. It would also be possible to get around this by having two identical 110 volt primaries and connect the either in parallel for the 110 volts or in series for the 220 volts. In this device, it's possible to fine-tune the set to the local mains voltage by 4 steps of 5 volts each. In the present time, the setting would be 220 volts plus 10 volts in Europe. In the secondary, we can see there are 2 secondary windings. The first one is the heater supply for the rectifier valve here. The second one has a center tap, which is tied to the ground potential. Then, the 2 ends of the winding provide alternating current in a total antiphase to each other. The antiphased currents are fed to the 2 anodes of the rectifier tube. The hot cathode then accepts the current from both winding ends. Most importantly, no current will flow towards the cold anodes, so the arrangement becomes a dual diode. It's now possible to substitute the rectifier tube by modern semiconductor diodes. The result of the rectification is a current that has both halves of the 50 Hz mains sine waves, effectively doubling the frequency to 100 Hz. This will be present on the rectified direct current as hum. Normally the hum needs to be minimized, but for instance when charging car batteries the hum is irrelevant. There's also an additional tap for creating a negative DC voltage for some of the circuitry, and there are 2 semiconductor diodes for it. In the 1950s, these were usually bulky selenium diodes. For removing hum, there are 3 main components: a heavy iron core coil with a large inductance and 2 smoothing capacitors. The coil will pass the direct current with only the internal resistance showing, but will resist the flow of the 100 Hz hum current. The 2 capacitors will give and receive current during the fluctuations, working as reservoirs. In this design, it was chosen to use relatively small value capacitors, since the designers feared the more common larger ones would have a limited life. Instead, the hum is reduced by an active system that sinks current through a separate power tube. Whenever there's a peak occurring in the hum voltage, the current sink will sink more current to ground against the high wattage resistor here. The opening of the sink is controlled by a voltage that is in antiphase to the operating current. The minimum hum is found by adjusting the trimmer here. In practice, there will be a considerable power dissipation in the tube, in the resistor, and the mains transformer. In the end, all the heat generated by the system may well have been worse than the fear of the higher value smoothing capacitors going bad. Some more delicate parts of the circuitry are receiving stabilized voltage through a resistor here. The voltage regulator tube will begin conducting at 250 volts, so the resistor and the sinking current at the regulator will find a balance, again generating more excess heat. Additionally, outside the picture here, There is a winding for the cathode heaters of the tubes, except for the rectifier tube. The voltage stabilizing tube needs no heating. These represent a rather high power, but are necessary for the tubes to operate.